Okay, so now we switch gears from definitions to actual protocols and results and some more open questions. And let me start. So we saw a simple example of a special MPC protocol. Let me show you what might be the simplest example for general MPC protocol. So if you want to explain to someone how a general MPC can work, this is slightly simpler than other alternatives I know. So let's start with this correlated randomness model, where we assume that in the offline phase there is this dealer that before the inputs are known, it distributes correlated randomness to the two parties. So we have two parties and a dealer. The dealer distributes correlated randomness from some distribution and goes away. And now we want, this is the model, right? Now we want the two parties to just securely realize functionality F where the output is given to the two parties. Okay, so how do we solve it? So if we were to talk about encryption, what would be your solution? One-time pad, right? So one-time pad is the simplest encryption scheme. You just give the same random string to the two parties and you encrypt by XORing your message with a string. So it turns out that there is something quite similar for MPC, right? So, and actually, you know, I don't know why it hasn't been observed before, but it's not only very simple, but it can also be practical for small things. You'll see soon what's good and what's bad about it. Okay, so what does the dealer do in the offline phase? Well, it takes the truth table of F, and it just shifts it both horizontally and vertically by random cyclic shifts dx and dy, right? So this G corresponds to the randomly shifted truth table, right? So if this is the original truth table, the function doesn't need to be a Boolean one. It can have non-binary outputs. Shift it by dx to the right, by dy down. Okay, that's the first phase. The second phase, just for specifying the distribution, is that I split this shifted matrix into two additive shares, right? GA and GB. GA goes to A, GB goes to B.
So this is only for finite functionalities?
So now we live in a math world, right? Yeah, it's for finite functionalities, yes. But you know, even in infinite functionality, you always reveal the input length, so you can... yeah, I mean, I will talk about the efficiency issues, but yes. If the truth table is too big, the protocol will not be something you can run, but for every finite functionality, it works, yes. Okay, so again, so Alice receives one part of the shifted truth table plus the horizontal shift amount dx. Bob receives the other part of the shifted truth table plus the vertical shift amount dy. Okay, this is the setup phase, and now the dealer goes to sleep. How does the protocol go? Yeah, as you might expect. So now the parties have inputs x and y, and the parties just exchange. Each party knows, the first party, Alice, she knows the correct column of the entry, right, that contains the output. It's just x plus dx. And Bob knows the correct row, y plus dy. So the parties just exchange these values. Then they figure out the correct entry in this shifted matrix, and they just exchange the shares. Okay, so every party just sends two messages, or if you want just one party to learn the output, then you have just two messages overall. Okay, so it's clear, right? You can analyze this in a few lines. You can use simulation, or you can use even just the information theory. And you can see that each party doesn't learn any information except the output, right? They just see a random shift coming from the other party, a random number, plus two random shares of the output. Right? This is what they can see. So you can trivially simulate it and prove it secure in whatever setting you like. Is it secure against the passive or active? What do you think is the case for active parties? Can they break the protocol? Or is it secure against active adversaries? What do you think? Well, it's trivial to cheat here, right? You can just, add one to the share of the table you're supposed to share, and you add one to the output. And this is not sometimes, for some functionalities, this is a legitimate attack, but for most it is not, right? So this protocol, as is, it is not secure against malicious parties, but you can easily augment it by using one-time unconditional max to be secure against malicious parties, assuming that the dealer is honest. If you want to protect against malicious dealer, this is more complicated. But if the dealer is honest, you can very easily, and again, everything is easy, protocol analysis, all self-contained, really something you can teach in class very easily. Okay, so what's good about this protocol? It is perfectly secure. I mean, I'm ignoring the fact that it needs this correlated randomness setup, but yeah, it's perfectly secure. It has great online communication. So what is the length? If each party has an n-bit input, how many bits does each party communicate? Something like input length plus output length, right? So it's for many functions it can be proved to be optimal. Right, there is some gap. If you can show that there are functions that have smaller communication complexity, and still you need this much communication. So it's not optimal for all functions, but it's optimal for most functions. This is really the best you can do. But as Vipul pointed out, this was what was bothering Vipul, is that the amount of randomness and storage, right, of the correlated randomness is proportional to the size of the truth table. So it's generally, it will be exponential in the input length. Yes. It is also one time, yes. But yeah.
How is it different from Faggy and Nao?
I don't see how it's related, but we can take it off.
Randomness and C
no, they have common randomness, and they have a third party which is a referee which learns the output. It's not.
They have correlated randomness. So if the dealer gives us correlated randomness,
they have identical randomness. They don't have correlated. If the dealer gives identical randomness to the two parties, they cannot even do OT. It's not. I mean, it seems the masking and shifting, the tricks are similar, but I don't see any technical way to derive one from the other. Okay, so right, so yeah, so this is the natural question is whether we can do better. It sounds like, so I don't know. What's your intuition? Do you think we can do better? So I'm just looking, we said in terms of online communication, it's great. The question is, what is the size? How much correlated randomness do we need? How much do the parties need to store? So let's see. Let's try to exercise our intuition. So we know that in order to hide the inputs, right? So the output is very small. The inputs are n-bit long. So we need at least n bits of randomness, right? This is the same type of intuition that shows that a one-time pad requires as much randomness as the message. This can be proved, right? So in this sense, we know something, right? Now, on the other hand, we do not really need to hide the truth table, right? The function f is public. It's well known. So there is no inherent reason why we will need as much randomness as the truth table, but still it might be tempting to conjecture that it's necessary, but fortunately this conjecture is false. So yeah, so I guess I was a bit premature. So let me first point out, this is also one answer to this question, that if we don't want a good solution for every function, but rather good solutions for efficiently computable functions, then, this is also something that we know is possible in almost every MPC model where we have a feasibility result. So we can just use, so suppose that the function has a small circuit. We can just define a small helper functionality for each gate, which will allow us to compute secret sharing of the output of this gate, given the shares of the inputs of this gate. This is a finite functionality. It's a randomized functionality, but as I said, you can reduce it to a deterministic one. So you can define such a finite functionality for each gate and give new independent fresh preprocessing material for each gate. In this way, you can evaluate a circuit using communication and randomness that is only linear in the size of the circuit. Okay, so this is a way to do better for computationally simple functions. And everyone here, I guess, is familiar with some version of this technique. We'll talk about it soon. And and again, yeah, for instance, if you look at the basic so-called GMW protocol, the history is complicated. You can ask Moti if he's here, I don't know, but he knows the history. But this is what everybody refers to as the GMW protocol, but it's actually not in the original GMW paper. This is the way of evaluating circuits using OT in a gate-by-gate fashion, which is a slightly different way of achieving the same result. So you can produce OT given finite amount of correlated randomness, and these two things are very similar. Okay, so now the more challenging question is, what can we do for arbitrary F, for the worst case F, right? So if you look at the worst case F, it doesn't have a small circuit, right? The circuit size is almost 2 to the n, slightly less, but certainly exponential in n. And the question is whether we can do better in terms of the amount of randomness. And here it turns out, and this is kind of non-trivial because it built, I mean, this is ours with Amos, Eyal, and Ranjit. We had a result from TCC 1 year ago that shows how to use any 3-server PIR protocol or 3-query LDC protocol towards getting a solution where the correlated randomness size is comparable to the communication. And this assumes some mild technical condition on the computational complexity of generating the queries in the PIR. So it might seem a bit odd. How can we use a 3-party, like if you don't know PIR, forget about it. But if you know PIR, there is this client and 3 servers. How can we use the 2 parties to emulate the 3 servers? Think about it. It's a simple but cute idea. So we can do it, and we can convert any 3-party PIR into a protocol with comparable efficiency, and this is the current world record of Efremenko for 3-server PIR, right? It's a super polynomial improvement, right? 2 to the n versus 2 to the square root, and it's a great improvement. And it might even be more practical than things like n squared for n, which is quite big, right? If you want concrete numbers. Okay, so. But the question is wide open. So the best thing we have in terms of lower bounds is just linear in n. The upper bound is 2 to the square root of n. So there are many problems of information theoretic cryptography where we are in a similar situation of huge gaps between the best known upper bounds and best known lower bounds. But this is, an innocent looking question. It looks like a generalization of one-time pad, wide open. Nobody knows the answer. And by the way, there is also a converse relation. So I would say that the complexity up to some technicalities, the complexity of this question, the answer to this question is morally equivalent to the question of PIR or locally decodable codes that many complexity theorists and coding theorists have looked into. Okay, so now it's easy to so previously we had the dealer. What if we want to have a protocol without a dealer? So let's use the previous protocol in a black box way to get a standard 3-party protocol where one party may be corrupted, right? Now there's no dealer. Now each of the 3 parties has its own input. What do? Well, we just define a 2-party functionality. So we want to evaluate a 3-party functionality G of X, Y, Z. We define a 2-party functionality where each of the 2 parties has an additional input, and we apply the 3-party on the first, on X and Y, and the sum of the 2 Z's, right? We define a 2-party functionality given a 3-party functionality. We take any protocol in the previous preprocessing model for this 2-party functionality, and we use it in the following way. So Carol will have 2 roles. First, she has an input, which she just additively splits, secretures between these 2 parties, Alice and Bob. And moreover, she acts as the dealer in the previous protocol, in the 2-party protocol. Okay, so she also generates these RA and RB as before. And now these 2 parties just evaluate F using the previous protocol, and it's easy to see that none of the 3 parties learn any information except the output. Okay? So now we already have the first, what you would call mainstream feasibility result. This is feasibility result. And again, we can do it linearly in the circuit size, right, as I mentioned before. So this is feasibility result like a BGW result for 3 parties, 1 semi-honest party, information theoretic model. Okay? Good. So, and it turns out, and this is a pretty cool stuff that Ron will talk about in the next workshop, that you can actually use this three-party protocol as a building block. So this, as it is, it doesn't seem to scale. So this approach, if you try to generalize it directly to, 21 parties, 10 of which can be corrupted, it's not obvious how to do it, but it turns out that if you combine some player virtualization technique where you emulate a player by protocol with a certain combinatorial construction of certain formulas that are not too deep, that compute the majority function, then you can bootstrap from this three-party protocol to an n-party protocol that tolerates, T less than K over 2 corrupted parties. There is some star. I will not get into the technicalities. Ron will mention it, but I guess relating to a previous comment I made, this is maybe, I mentioned that some information theoretic results are conditional. This is one such example, or at least some variants of this approach are conditional. Okay, so let me, for completeness, I want to give a very broad overview of what are the main techniques we have for achieving security. I will start with the passive case or semi-honest model, and then talk about the active case. But let me start by trying to give, I'm sure it's not a comprehensive, but at least it will cover the main approaches we know to realize MPC in the passive setting. So perhaps, so I start with the information theoretic setting where we have an honest majority in point-to-point channels. Then the well-known to anyone who knows this concept of MPC, know of this BGW protocol, which was together with a concurrent protocol by Chaum et al. This was the first protocol to establish the feasibility of MPC with an honest majority. And the idea is not very complicated, but it uses a little bit of algebra, right? So it uses Shamir secret sharing, which is a way to share secrets using polynomials. If you want to hide the secret from T parties, then you pick a random degree T polynomial that evaluates to the secret on 0. And now you exploit this so-called multiplicative property. So this can be abstracted to general secret sharing schemes. You can define a multiplicative property of general secret sharing schemes, which this specific secret sharing scheme satisfies. And this multiplicative property says, in its general form, that if each party takes a share of his share of secret X and his share of secret Y, multiplies them locally, no interaction, then the outputs of this process, the K outputs of this process, can be linearly combined to give the product of the two secrets. Right? Why is this true for polynomials? Because if you take a degree T polynomial with free coefficient X and a degree T polynomial with free coefficient Y and multiply them, you get a degree 2T polynomial with free coefficient X times Y. Okay, and now you can use a linear combination. If you want, you can use it to reconstruct the secret, but if you want, you can just use it to reduce the degree. So it's kind of like a simple version of things that are done also in the context of FHE, except that here it's all much simpler, no noise to worry about, and we use interaction to reduce the degree. So reducing the degree uses a protocol that computes a linear function. As I said, reducing a degree of a polynomial while maintaining its free coefficient is a linear function. And basically the protocol that we saw in the beginning of the talk for addition can be used to get, so the first round of this protocol can be used to compute any such degree reduction, or a simple generalization of this protocol. Right, so basically the high-level approach is we take our computation, we represent it as an arithmetic circuit with additions and multiplications over the field over which secret sharing is defined. So in the case of Shamir secret sharing, it will be a non-binary field, but we can take any binary circuit and write it as an arithmetic circuit over whatever field that we like. Now we start by having each party secret share his input using Shamir scheme, and now we proceed gate by gate. Whenever we have a gate ready, in the sense that its two inputs have been secret shared, we can apply this local multiplication and one round degree reduction to compute shares using the same degree of the output of this gate. And this process will result in a protocol whose overall communication complexity is linear in the circuit size, also quadratic in the number of parties, which can be significantly improved, but it grows linearly with the circuit size. And the round complexity will be proportional to the so-called multiplicative depth. So it's kind of like depth of the circuit, or the length of the longest path from an input to an output, where additions are not counted, only multiplications. Just because you can evaluate things in parallel. Okay, what about the case where we have no honest majority, but we still want information theoretic security in the OT hybrid model? This is a so-called GMW protocol. And it uses a similar principle, but it's a bit simpler. So we can use additive secret sharing. I mean, that's essentially the only type of K out of K secret sharing we have, or the useful one we have. We use this XOR secret sharing. So we split every input bit into K random bits subject to the restriction that their exclusive OR is the input. And now we can use the OT calls. Again, it's very simple, but I'm not going into the details because, I guess that many of you know them already, but we can easily use the OT oracle, a single round of calls to the OT oracle, to move from secret sharing of two inputs of a gate or nonlinear gate like an AND or an AND to having a fresh secret sharing of the output of this gate. And additions or XOR operations are for free. So if you have a circuit over the standard Boolean basis, you need to spend the round for every layer in which you have some nonlinear gate. XORs are for free. And by the way, this protocol, again, if you implement it, and it has been implemented, and combine it with actual state-of-the-art implementations of oblivious transfer, it's super fast. Right? It's really, really fast. So for the passive security model and for functionalities that are not too deep in terms of the circuit size, this thing is really, really, really fast. Okay, so let's move now to something that Benny will talk about extensively later today. This is something known as randomized encodings, or perhaps in a narrower sense, it's known also as a garbling scheme or garbled circuits. And the high-level idea, which again Benny will talk about, I guess, extensively, is that so if you look at the previous two protocols that I mentioned, they both work better for simple functions, where simple in this sense means low multiplicative depth or low algebraic degree. Right, so the round complexity is proportional to the multiplicative depth. So we obviously would rather evaluate functionalities that are shallow than ones that are deep. And the high-level idea of these types of encodings is to take a complex f that has a high depth and replace it by a randomized function f prime, which is in a sense equivalent. Its output is a randomized encoding of the output of f, and it turns out that these things can be done in a way that makes f prime much simpler. And simpler could be, typically in the classical uses of this, simpler meaning having much smaller depth. Okay, so again, I don't want to get too much into Benny's territory, but if you look at these constructions, they can basically, you apply some complexity result of encoding functions with the previous protocols, and you get constant round protocols. And just to tell you a little bit about what you can do, again, I'm referring to the previous protocols that I mentioned. I'm not, so if you combine the previous protocols that I mentioned with the best known randomized encoding techniques, you can get protocols. Again, we're talking still about the passive adversary point-to-point channels. So this is one of the frustrating open problems, that we cannot get simultaneously minimal round complexity, which is 2 rounds in this setting, and maximal resilience, which is t less than k over 2 in this setting. So we can get either 2 rounds with slightly suboptimal resilience or 3 rounds with optimal resilience, right? And this is, again, information theoretically. And in the computational setting, so this notion, of course, most people are familiar with it in the context of garbled circuits, which is a computationally secure randomized encoding or garbling scheme. This has the big advantage of being, so I did not mention that these information theoretic techniques only work for functions that are, say, in NC1 or in log space, non-deterministic log space, efficiently, right? You can do it for any function, but if you want things to be polynomial, you need to restrict yourself to relatively, not too deep functions. In the computational setting, using only a PRG or a one-way function, you can use Yao's garbled circuit technique to get protocols that scale, that work also in the two-party setting, and they use they work efficiently for all circuits.
So you only get this information theoretically. If I want like a function in B, what is the best round complexity? Or is it conjecture?
Yeah, so there's a trade-off between communication and rounds. If you don't care about communication, then complexity of the function doesn't matter. So this is the best.
If I want to do, polynomial time, if the function is polynomial time, I want to do polynomial communication. Can I do it in constant rounds? So is it known?
No, the best known thing is to basically cut your circuit, to chop it into log depth slices and use these information theoretic techniques for each slice. You can save a logarithmic factor. That's the best known, yeah.
Is there a low bound or some conjectured impossibility or anything?
No, not that I know of. Conjectured impossibility. There is some guy who conjectured impossibility, so there is, yeah. Okay, so good. And by the way, this 2-round, 4-round, this refers to an actual implementation of the OT by a 2-message protocol. So this is not in the OT hybrid model. This is a computationally secure instantiation. And again, Daniel, I will mention a result that was mentioned in the obfuscation session that now using, now you don't need obfuscation, but using LWE, this is Daniel's new result, and the CRS. You can get 2 rounds with t less than k, but this is computational setting, and also the assumption is somewhat stronger, and there is a CRS. But this result assumes 2-message OT, which is kind of a more liberal assumption. Good. And recent I/O-based constructions of succinct garbling things and similar creatures, which I assume that Benny will mention, allow us to save not only rounds, but also other complexity measures that previously we did not know how to save. Again, computation, we cannot avoid that somebody has to do the computation, right? I mean, you cannot use, even I/O cannot speed up computations, but you can move computations from one party to another. In all these protocols, everybody basically needs to do the work, but you can move work around. Okay, so, and there's been really an enormous body of recent work on getting all kinds of concrete, especially concrete, a little bit asymptotic, but mainly concrete optimizations in implementation of the main garbling technique due to Yao. And I'm sure there will be talks about it in the next workshop. Okay, so yet another approach to MPC, which actually dates back to 93 or possibly earlier, is to use homomorphic encryption. What kind of homomorphic encryption? I don't think we even heard about it in this workshop, but what kind of homomorphic encryption did we have during most of my research career, right, until 99? Till 99, you said homomorphic encryption, you referred to something like, I think in the formulation of Ron's result that we mentioned, we had this notion that you can add things, right? So this is linearly homomorphic encryption, and actually this was used, and also a threshold version of it was used to implement MPC with similar performance characteristics to the OT hybrid model. The advantage was perhaps getting the dependence of the number of parties to be not quadratic but linear. On the downside, and that's a huge downside of this approach, is that they require a public key crypto for every gate, whereas protocols in the OT hybrid model, we can amortize the cost such that the bulk of the work is just symmetric crypto. So this is why these protocols are not very popular these days. Gentry's breakthrough made it, compress the communication. The TFHE further reduced the round complexity. The previous 4 was reduced to 3 using threshold FHE. And now using multi-key FHE in the CRS model, we know that we can get 2 rounds, which is optimal. Okay, and there was an additional approach, earlier approach for 2-round MPC using I/O, which for now isn't subsumed by the LWE basing, but I'm sure that the ideas will find. So I/O is a stronger primitive and can lead to stronger results in certain settings. So for MPC. Okay, so active secure MPC is a much more challenging goal. Why? Because we need to account for every possible deviation from the protocol. Right, so analyzing passive attacks is kind of easy. You just look, in the information theoretic setting, for instance, you just look at 2 distributions, you check that they're the same. In the active case, you really need to account for every possible attack, and also the ideal model becomes more complicated because now the notion of security allows the adversary to pick any effective input. So you need to worry not only about technically, what the simulator needs to do is extract an effective input from the adversary such that all it learns can be inferred from or can be simulated given the output of the function on this input and the inputs of the honest parties. So things are much more complex. And I think that it's been really a major endeavor in cryptography, both in the theoretical research and this implementation community, to minimize the overhead of protocols with security against active adversaries. So there's been a lot of progress, but still quite significant gaps. So a common paradigm is to start with a passive secure protocol and somehow compile it into a similar protocol that resists active attacks. And this dates back to the seminal work of GMW, which introduced this beautiful idea of using zero-knowledge proofs for this purpose, right? So the idea is that we take a protocol. This applied only to protocols in the computational model because they required communication to be public, right? You need to prove statements about something that everybody observes. So take any protocol that works over public channels, and now you use zero-knowledge proofs to prove that the next message you send is consistent with the protocol, but the problem is that the protocol involves some secrets, right? So you first need to commit to your input, you need to do some coin tossing, so you generate some committed coins, and now you prove once this setup has been completed, you use zero-knowledge proofs to just prove that you're sending the right thing. And everybody can see if you're lying and abort the protocol. So it's really using the notion of zero knowledge in an unexpected way. Now we take it for granted, but it's a really amazing application of this notion of zero knowledge proofs, which is very interesting in its own. But this shows us that we can take any protocol and compile it into an actively secure protocol. Just force parties to follow the protocol without revealing any of their secrets. Okay, so this is one approach that has been very dominant still in most of the theory literature, unless, say, you're interested in black box constructions, which Ale will talk about, I guess. People just prefer to use it because it's a very general thing that you get almost for free, in theory. Okay, another approach that has been, as I said, this doesn't apply to information theoretic protocols because of the use of secure channels. So the initial approach in this information theoretic setting has been to make sub-protocols verifiable. So if I'm supposed to secret share my input, you cannot verify that I shared my input because I can choose whatever input I like. But you can verify, or the community can verify, that the shares I distributed are consistent with some valid input. And this is done by a so-called verifiable secret sharing protocol, and there are various creative solutions to this problem that are kind of hairy, especially if you want optimal resilience. They're much simpler if you settle for resisting slightly less than optimal threshold. And if you're happy with resisting square root of the number of bad parties, then it becomes really trivial. So I don't have time to show it, but you can show super simple protocols if the number of parties is at least quadratic in the security threshold, and they are honest majority, like big honest majority protocols that offer security against, and are polynomial also in the number of parties, and they offer security against malicious parties. But this is a really small threshold. The closer you get to optimal, the more hairy these protocols. So it's not only VSS, you also need to have a multiplication sub-protocol, and there were some unclarities about the original BGW paper, which a paper by Tal and Yehuda and Gilad, or just Yehuda resolved. So these things are very complicated. I'm sure that BGW had at some point the right thing in mind. I don't know, did you talk to them? But in any case, the details were very hard to extract from the original paper, and this indicates that really these things are quite hairy. Okay, nowadays when people implement protocols based on garbled circuits, they mostly use cut and choose techniques that originate. There was an earlier paper by Mohatzel and Franklin, and then I guess that the first paper that gave a full proof was a paper by Lindell and Pincus that showed how it's not trivial. There are many subtleties. It's a cut and choose approach, which is tailored in an ad hoc way to protocols based on garbled circuits, and makes these protocols secure against malicious parties. To date, by the way, in terms of overhead, if you want security of 2 to the minus sigma, sigma is some kind of probability of catching cheating. 2 to the minus sigma is the probability of catching cheating. The best known practical approach has an overhead of sigma, multiplicative overhead compared to the passive secure protocol, the basic garbled circuit. Asymptotically, you can reduce it to polylog sigma. So there is a work with the ICOS gang and Manoj, Eyal, Rafi, Amit, and Manoj that reduces the overhead to polylog. Okay, perhaps but the most recent approach I mentioned is something that is originated from a joint work with Daniel Genkin, Eran Tromer, and Manoj and Amit. And this approach basically says the following. Let's say that we run these very simple semi-honest secure protocol that I described. So passively secure protocol that I described. This is simple BGW for passive case, simple GMW. And now let's ask ourselves what goes wrong, or how bad things are if the adversary is active. So if you analyze things carefully, it turns out that everything that the adversary can achieve, both in terms of information it learns and effect it has, influence it has on the outputs, can be captured by a so-called additive attack, where additive attack means just that the adversary can pick, if it's an arithmetic circuit, it means that the adversary can pick a fixed field element to be added to every wire in the circuit. Blindly, completely blindly. This is basically what captures the full power of a malicious attack on such protocols. In the Boolean case, it's like toggling an arbitrary subset of the wires. And then the question reduces to a complexity theory question of designing circuits that resist this very limited type of attacks. And it turns out that for arithmetic circuits over large fields, this can be done with a small overhead. And the same approach has been independently pursued by Karashi et al., who actually, I think, also implemented it and figured out that I think they have a factor 8 or less gap between semi-honest and malicious for Rabin-Ben-Or style protocols. So if you want 3-party, one of them is malicious. The semi-honest is super duper fast. This is basically what I described. Malicious using this approach is only 6 to 8 times faster. And in an upcoming crypto paper with Daniel and Antigone, we actually extend this approach to so-called SIMD circuits that do things in parallel, which gives better asymptotic performance and also has the hope of getting even better practical efficiency. So this approach, in the case of honest majority protocol, which, as I will argue, are interesting beyond the case of honest majority, this approach has a promise of really helping things run faster. Plus has some asymptotic advantages as well. Right, so finally I will describe now, I guess that in most of the remaining time, I will describe an approach coined as MPC in the head, which can be used to achieve various things, among which is leveraging or taking simple protocols, including passive secure protocols, and using them to build active secure protocols. Okay, so that's a pictorial picture of the technique. So again, let me recall these, let's again take this nostalgic tour of the 1980s, those previous days of Gold Rush, prior not Gold Reich, but Gold Rush, prior to obfuscation. There was a lot of excitement. They basically could do everything that obfuscation can do and more, but allowing interaction, right? Obfuscation, function encryption, all that is about doing things without interaction. So it started perhaps with zero-knowledge proofs, this amazing result using very clever, right? So if you look at the textbook proof that people teach of zero-knowledge proofs for NP, they rely on NP completeness of 3 colorability, which is something that takes quite a lot of time to teach in class. So it's like we were extremely lucky that we had this 3 colorability problem that happens to be NP complete, and you can use it to get zero knowledge in a natural way. So this was the first result in this sequence. And you had then you had this sequence of feasibility results that I mentioned. So in the computational model, there were feasibility results for MPC with no honest majority, also in the case of malicious parties. And then later came the results for unconditional or information theoretic MPC with honest majority. And later came, and again, this was a pretty hairy result at the time, you know, pretty complicated by Kilian that showed that you can get, so what I described is how to use OT to get information theoretic security in the passive model. The active model was much, much more complicated, right? You can look at the Kilian thesis to figure out. And the question is whether these things are really unrelated. So each introduced a bunch of new tricks. It's not like these papers look the same. Each of them introduced a whole lot of new ideas. And basically what motivated this effort is the attempt to kind of minimize the description complexity, to compress these seminal results into fewer things we need to know about. Okay, so the message is that one type of message I would like to make now is that honest majority MPC is useful even if you only care about secure two-party computation or in general MPC with no honest majority. Okay, so that's something to keep in mind. So in particular, if you improve the state of the art in honest majority MPC, this, at least there is a possibility that this will also reflect on two-party computation. It establishes these initially unexpected relations between the classical results. It gives us some new results, especially in terms of asymptotic efficiency for MPC with no honest majority. And also, I think it also made some people working on algebraic geometric codes very happy because it gave, these algebraic geometric codes are very useful in the context of information theoretic honest majority MPC, and nobody was interested in these things, but now you can at least claim, you know, whether it's true or not, that you can transfer these results to, you know, zero knowledge, two-party model. You indeed can. You get new asymptotic results that were not known before. And this kind of is good for science because it kind of further motivates these very relatively deep branches of mathematics and coding theory. And again, what are algebraic geometric codes? If you never heard about them, these are just like the Reed-Solomon codes that are used in Shamir secret sharing. So you can think of something similar to Shamir secret sharing, except that the field size is constant. It does not grow with the number of parties. And the only downside is that you pay a little bit. You don't get now the optimal resilience of t less than k over 2, but you can get t less than 0.49 k. So you pay a little bit in the fractional resilience, but in return you improve the asymptotics. You get rid of a log factor. Okay, so let me remind you so the first application I'm going to describe is to zero-knowledge proofs. So I'm going to show, let me start by recalling what zero-knowledge proofs are. So this is going to be some alternative to the GMW general zero-knowledge proof from NP. So let me remind you what zero-knowledge proof are. So for cryptographic purposes, where we want the prover to be efficient, it's we typically focus on an NP relation that can be verified by polynomial time predicate R. So it takes an input and a witness, and it tells us whether the witness is indeed convincing, whether it's a valid proof that X is in the language. We have the usual notions of completeness, soundness, and zero knowledge. And we want to use MPC, an honest majority MPC. You know, it can be information theoretic. It does not have to, but it can be information theoretic because it's an honest majority MPC towards building such protocols. Right? So the first step is something similar to what we did before. We define this new helper functionality. So, you know, this is just a relation. It's a two-argument function. We don't even think about it as a functionality, as a mapping from inputs to outputs. We use it to define a functionality G that has a public input X. So public inputs, I did not mention it, but it's easy to incorporate them into the MPC model. That's the statement that you want to prove. Plus, it takes n strings of the same length as the witness, one from each party. It XORs them and outputs the result of the verification R. Okay, this is now an n-party functionality. And now we use any MPC protocol which is passively secure, right? Again, passive attacks. It's secure against two parties, and we also, for technical reasons, need it to be perfectly correct, so have no error probability for this augmented functionality G. And again, this is possible when we have an honest majority. So if we want security against two parties, we need to have 5 parties. But we can use the 5-party BGW protocol that I described briefly before. Okay, so now how does the zero-knowledge protocol go? This is a joint work with Eyal, Rafi, and Amit. So we're given this honest majority MPC protocol for G, right? The first thing the prover does, the prover holds this witness W, which he wants to keep secret. The first thing that he does, he breaks W into n shares. Okay, additive shares. They XOR to W, they're otherwise random. Okay, now it assigns each of these shares an input to the functionality G to a different party, and just runs in his head the MPC protocol on these WI. So the purpose of this MPC protocol, the output of it, will basically be the result of verifying whether RXW hold for W, which is defined to be the XOR of these inputs. Right? This is what the functionality computes. Okay, so this protocol involves a lot of messages potentially between the parties, but this is all done in the prover's head. And now, as a result of this interaction, each party has a view. We denote it by VI. The view of a party consists, without loss of generality, of its randomness, its local randomness, its input, and the incoming messages. Outgoing messages are determined by this information, right? That's a canonical way of presenting views. Right, so now what the prover does is commits to these views. Right? For now, for simplicity, think of the commitment as being just an oracle, right? It's an ideal commitment, but you can actually replace it by an actual cryptographic commitment. Okay, so it commits to each view separately. What does the verifier want, right? So the verifier will be happy if this MPC protocol returns 1 as an output, right? Because then it means that there are some shares of a witness, right? It must be some value, it must be something, right? It's an XOR of some string. So even if the prover cheats, there is basically no cheating space in secret sharing, additive secret sharing, right? So there is some string W that makes the relation evaluate to 1, right? So this is what the verifier wants to be convinced of. So what he does, a natural thing to do, is to just pick at random a pair of views and ask the prover, please reveal these views you committed to, right? So the prover opens these two views, 2 and 5, which the verifier picked. And what does he do? He accepts if, first of all, both of these parties, 2 and 5, the output in the MPC protocol was 1. The output is, again, part of the view or is inferred by the view. And moreover, these two views are consistent in the sense that the incoming messages explicit in one of these views are identical to the outgoing messages, the corresponding outgoing messages that are implicit in the other view. Okay, I mean, you can implement it in various ways, but basically this is the natural consistency requirement, that the things that should be in common to the two views are indeed in common. And the crucial point about this consistency is that if you have these pairwise consistencies, it's kind of like local testing, right? If you have if all pairs of views are consistent, then they must be globally consistent, right? It's an easy proof. It seems obvious, but you actually can prove it by induction, right? So if all pairs are consistent, then everything is globally consistent with some valid of the execution of the protocol on some inputs. Right, so now we can analyze this protocol using this observation. So completeness is easy. If the prover is honest, the verifier, everything will verify correctly, and this is easy. The zero knowledge is also quite easy because we assume the MPC protocol to be secure against two passive parties, right? So if you just look at two views, they contain no information about the witness. Okay? So yeah, and for this we note that we applied this secret sharing. So it was enough to actually, we didn't need to secret share the witness into n parts. It's enough to secret share into 3 parts because we just need that every 2 shares of the witness will not reveal anything about the witness. Okay, the more interesting part is the soundness, right? So suppose that the statement is false. This means that for every W, the relation evaluates to 0. Okay, so what it means is that the prover has 2 options. Either he runs the protocol correctly on some valid inputs W1 through Wn, in which case the output of the protocol will be 0. That's the first case, right? In this case, all outputs will be 0, and the verifier will always reject. Right? Here I'm relying on the perfect correctness assumption. The other option is that the prover commits to some views which are not consistent with any valid execution, and by what I said before, there must be at least one pair of inconsistent views which will be detected with constant probability. I'm assuming here the number of parties to be constant, and then you can amplify soundness by repetition. Okay? So it turns out that you can extend it in various useful ways. So you can use protocols in the OT hybrid model, like the 3-party GMW protocol that I described. And the pairwise consistencies, you just need to check that things that are reported on both sides about the use of the common OT oracle are consistent. So this will work, and this is in fact simpler than a 5-party BGW. A 3-party GMW is very simple and lean. It will give very lean zero-knowledge protocols. You can also have a variant where you just need to use a 1-secure MPC, say 3-party BGW. But then you also need to commit to the channel. So there is some trade-off, and you need to open at random one view in one of the incident channels. Okay, it's a different version of this approach. And you can also extend it beyond perfectly correct MPC protocols by using some more rounds. Okay, so perhaps the more interesting variant, both technically and in terms of potential applications, is something that avoids this naive repetition, right? So this naive repetition means that if I want 2 to the minus s soundness error, I must repeat some basic protocol s times, which is not what we want. But it turns out that if I use MPC protocols with many parties that are robust against many malicious parties, say 1/10. It's still much easier than the protocol that you have. I don't need optimal security threshold. I just need significant level of security, say any constant fractional threshold. Then you can show that you don't need to amplify soundness by repetition. You can use a simple graph theoretic argument to show that if you open as many views as you can, so up to the security threshold, you will catch cheating now with overwhelming probability. And the reason is that now, because of the robustness of the MPC protocol, now it has to be secure against malicious parties, if I did not mention this. Because of this robustness feature, it means that if you want to violate soundness, you need to cheat in many places. The cheating, the inconsistency graph, should have a big vertex cover, minimal vertex cover, which means you can analyze it, that you can catch cheating very well, even at one shot. So this asymptotically gives us the best protocols. And something interesting, that even though we consider MPC protocols with many parties, we can use convenient protocols. So we have here just two clients. One has the inputs, one has the output, and many servers. So this simplifies things in terms of the MPC model. So the adversary only corrupts a single client and up to T servers. Another simplification is that we don't need guaranteed output delivery. It's enough to get security with a board. So this also simplifies protocols. And broadcast is for free, because you can include just whatever. The prover does it all in his head, so he can take the broadcasted messages and just post them once. You don't need to broadcast. And as I said, we can get it, we can make the ideal commitment actually implementable by using a 1V function. Okay, so I will skip. So the applications, again, bias both simplicity and some asymptotic efficiency improvements. I should say that if you just use, so some of the results we had were later improved by GKR, the paper that Yael mentioned, but this applies to not results that are mentioned here. So we had some additional applications that had to do with getting below the circuit size for certain simple functions. So this I'm not mentioning here, but basically the main new application we get here is constant rate zero knowledge, in the sense that, first of all, they're all unconditional in the hybrid model or using 1V functions in the plain model, and the length of the proof is just constant times the size of a circuit. Right? So this is something that is based on these MPC protocols that rely on algebraic geometry codes, and that's one of the new applications we have. And another type of application beyond the simplicity and maybe good concrete efficiency that we get here is that we can now build on the large body of work on all kinds of MPC problems. So there is a lot of work on MPC for linear algebra problems or other natural problems. And this many of these works refer to MPC with honest majority and use all kinds of tricks that are relevant in the MPC context. And now you can apply these things in a black box way to get zero knowledge proofs for the same types of problems. Okay, how much time do I have?
2 minutes.
2 minutes, okay. So let me really briefly describe what is known now as the IPS compiler, which is joint work with Manoj and Amit. And this is basically, in a way, it is some black box version of the GMW compiler. So the GMW compiler is highly non-black box in that you need the code of the passive secure protocol you're compiling, and for every atomic operation in this code, you replace it by crypto. So it's non-black box in that you need the code, and it's inherently inefficient in that you replace every basic operation by it's not inherently inefficient, but it's typically inefficient. And basically what the result shows is some version, it doesn't give you the natural version of a black box way of moving from passive to active security, but it gives you some augmented version where the upshot is that you can get secure two-party protocols, or in general, multi-party protocols with no honest majority, by combining in a black box way two much, much simpler ingredients that are easier and more efficient to construct. One relaxes the goal by assuming an honest majority. So this is an outer protocol, which is an MPC protocol that can have a big honest majority, but it has to be secure against active attacks. It's much simpler because there is an honest majority, so these results, are much simpler than Killian, right? It's a lighter version of BGW. And the other type of protocol is the same type of protocol we're trying to construct, except that in the passive model, we've seen such a trivial protocol, the GMW in the passive case, OT hybrid model. It's a very, very simple and efficient protocol. And basically, you inherit the simplicity and efficiency features of these two components because their combination is very lean. And this is just a picture. You can view it as some kind of a generic form of cut and choose, where you obliviously watch, you do a virtualization of every party in the multi-party protocol between these two parties, and you kind of do these random, what we call watch lists to catch cheating. And again, this type of combination is very lean. It introduces almost no additional overhead, not asymptotically, not concretely. Okay, so let me jump. Can I just get to the open questions part? So. Or no? What do you think? Okay, so I'll get directly to it. So I meant to speak about the communication complexity of information theoretic MPC. I will just conclude with the open questions. So now I'm following the footsteps of giants, of Craig and Vinod in the ratio between what I covered and the amount of slides. So
do you think you're doing better?
I don't know what is better. Is preparing more slides or okay, so yeah, let me mention some. Again, this is a really partial sample of open questions in the context of information theoretic MPC and computational MPC. So again, information theoretic MPC, you need to remember that FHE does not apply and IO does not apply. Okay, these are just when you think about open questions disappearing, information theoretic MPC is untouched by these things. There were other developments that I mentioned, but all this recent excitement is irrelevant. So in terms of communication complexity, as I mentioned some version of the problem, but you can consider basically any information theoretic model that you like, and the questions have a similar flavor. And the results, the known results and the gaps have a similar flavor, not identical, but similar, right? So we have three types of questions. In the high end, we want to understand the communication complexity of the worst functions, right? So, is any function, now you can think of worst functions, who can compute even without security, we cannot compute the worst function. This is not true because many useful functions have polynomial size input domains, so we can compute them. So this is a relevant question. So we have this gap. This is the best known lower bound, and this is the best known upper bound. Previously, I mentioned 2 to the square root of n, so this square root of n can be made cubic root, fourth root, if you use more and more parties. It's kind of, the number of parties needs to grow exponentially right now with 1 over epsilon, but you can get basically 2 to the n to the epsilon with a constant number of parties. That's for the worst types of functions on n input bits. And this is, as I mentioned, closely related to these other questions of private information retrieval and locally decodable codes. I guess we should have a makeup lecture on private information retrieval because I really wanted to cover this, but not this time. Okay, in the mid-range, you can say, okay, so we get these very significant savings for the worst functions. What about normal functions that take a cubic time to compute? Can we get savings in this range? And the answer is that we don't know anything. So we cannot translate these savings at the high end into anything for, say, polynomial size circuits. We don't know. So the best we're still stuck with is circuit size. That's the best communication complexity in essentially any reasonable information theoretic model. And on the low end, there are some questions about the constant. So if we want to implement many copies of a finite functionality, say using OT, there are some works, including by Manoj and his brother Vinod. The other Vinod is an information theorist, and by Maji and others, and Amit, on trying to understand what is the best constant that can be achieved when you want to reduce one finite functionality to another. It seems like a very different type of questions. Okay, round complexity, big, perhaps the best known open question. We know how to get constant round protocols for simple functions like NC1 or non-deterministic log space. Again, I guess that Benny maybe a little bit. Okay, not? Okay. So the big question is whether we can extend it to polynomial time computable function. This is related to the topic of Benny's talk. If we had these information theoretic garbling schemes for polynomial time function, then the answer is yes. The converse, we don't know. We don't know that this implies a constant round. We don't know whether interaction is helpful or not. More interaction. And the smaller annoying question I mentioned, can you get optimal round complexity with optimal resilience? We can almost get there. We don't know. This is open. In terms of computational complexity, you can ask, suppose that I have many parties. I want to evaluate, say, a big circuit. What is the minimal ratio between the circuit needed to implement all parties together? You can ask it in other models, but I'm talking about circuits now. And the circuit required to compute the function without security. There have been some relevant works. The best overhead we have is polylog in the number of parties. This seems to relate to questions, in coding, difficult questions that we don't know the answers to. And if we manage to get this polylog down to constant, then we can translate these results to zero knowledge proofs again, and two-party computation, which we have in a hybrid model or even in the plain model under computational assumptions. We can get polylog overhead, where here polylog isn't a security parameter. Okay, I guess I can take another minute for the computational model. Okay, very good. Okay, computational MPC. Gentry's FHE was really a blow to all of the people who tried to do a career studying communication complexity. So before Gentry's result, there were all these results on this specific function under these assumptions. I mean, the big question about communication complexity of crypto were essentially solved by FHE, modulo some issues. But FHE basically tells us that we can take anything we can do with a certain communication complexity, and we can do the same thing security with comparable, roughly the same communication complexity. There are still some gaps. One gap was recently closed by Daniel Wicks and others, where he addressed some overlooked case of functions with a big output. This requires I/O, so FHE is not enough. But even if you look at functions like with short output, say n-bit input, n-bit output using FHE, we don't know how to do it with order of n communication complexity. We can do it actually under some phi hiding. It's non-trivial. We can do it for linear in the circuit size. So now if you have linear size circuits, or generally you want a secure two-party computation where the communication complexity is just a constant number of bits per gate, you can do it either under phi hiding assumption or assuming a polynomial stretch, say quadratic stretch, pseudo-random generator in NC0, so with constant depth, which is something that Benny worked on and gave us more reasons to believe that these objects exist. So we have these two incomparable assumptions. Getting a similar result under a different assumption is quite interesting. There is this thing that Telet mentioned. I think it's a really cool problem. Again, I will not get into it, but it's related to this notion of function secret sharing based on one-way functions. We can do something very good for two parties, not for three parties or more. Round complexity, diversifying assumptions for two-round MPC, eliminating CRS, which I mentioned. And computational complexity, this is what I just mentioned. So with constant okay, this is a different question, but with constant computational overhead, the only thing we have right now relies on these strong PRGs in NC0. We don't have any other assumption or even heuristic construction that achieves just a constant number. Now I'm talking about the number of Boolean operations you compute per gate if you want to securely compute a function. So constant overhead means efficiency gap between insecure computation and secure computation is just a constant factor, not polylog factor that can be done using fancy versions of FHE or other techniques, but constant factor. This we only know under a single assumption, polystretch PRG in NC0. And finally, there is a lot of work these days, and I assume many open questions still about MPC in the RAM model. First study by Rafi and Shoup, and nowadays it's a really the combination of MPC and ORAM And now it's a really large research area, which we'll hear about from Elaine tomorrow. Okay, that's it. Thank you.